Alright, so hi guys. This lecture is going to be about random forests, which build upon the topic that we discussed last time, which was decision trees. So random forests are something called an ensemble method, which is basically a collection of many individual machine learning models. And specifically, a random forest consists of many small, unique decision trees, and all these decision trees vote together to come up with a final decision that's outputted from the random forest. And so, it's called a forest because it's like a collection of trees. That's just something interesting. Um, and so usually random forests tend to perform better than an individual decision tree because having several smaller decision trees helps prevent overfitting rather than just try to create one big decision tree. We discussed overfitting last time. Overfitting is basically when you learn the training data too well and you're not able to generalize whatever you found in the training data to your testing data. And so using a random forest usually helps prevent this issue. And so you can see in this diagram, if you're trying to predict the color given like pixel values of an image, for example, um, and you feed it into your random forest will feed in all the data to each and every one of the decision trees that are in it. And then each of these decision trees will output what it thinks is the proper classification. And then you just have to aggregate all of the votes together and then see, okay, what is the most common vote? And in this case, it was blue. So there are several hyperparameters of random forest that you need to select before getting started. Hyperparameters are basically um, settings of a machine learning model that you have to set before you let the machine learning model go ahead and train. Um, so these are something that we have to do before training. Um, the three main hyperparameters of random forests are k, which is the number of decision trees that we train, n, which is the size of our bootstrap sample for each decision tree. I'll talk exactly about what bootstrap samples mean and where we use them. And then d is the number of features that we allow each of the individual decision trees in our random forest to train on. And so I've listed some possible considerations for selecting these hyperparameters. So for k, the more decision trees you have, the more time you'll have to spend like training for training each and every one of those decision trees. And so having higher values of k will require higher compute power. This is not a terrible downside because decision trees are usually pretty easy and quick to train, but this is just something to note. I'll talk exactly about what our bootstrap samples mean, but um, a larger n may increase the overfitting, which is the kind of thing that random forests were supposed to prevent. So usually you want to try to strike a balance between an extremely large n and an extremely small n, because an extremely small n will lead to a drop in performance. I'll come back to this slide once I finish discussing an example. So let's walk through creating our random forest from this data set. So we have k equals 6, so we're basically going to, our random forest is going to be a collection of 6 different decision trees. And our size of bootstrap samples is 5, and the number of features that we use to train the decision tree is going to be 3. Okay, so this is our original data set, and we want to create 6 decision trees that all aggregate their decisions together, and then we get a final output from this entire random forest. So this is our data set. And so let's start off the process of creating a random forest by first finding a bootstrap sample. So a bootstrap sample is just a random set of the original data set that is selected with replacement, right? So let's say we previously set n to 5, so we want 5 entities in our data set after bootstrapping. So basically, for 5 times, we randomly select one of the values in our original training set and just put it in our new bootstrap sample, right? So the first time we randomly select one, we put one in, right? The ID one, and then this corresponds to um, some entity. If this was like uh, cancer, like predicting whether a tumor was malignant or benign, these could all be characteristics of the tumor size, and then -1 would be it's malignant, and then +1 would be it's benign, right? So this represents the data coming from one tumor, and so we randomly pick a row from our training data set and put it in. Uh, and we keep doing this until the total number of entities in our new bootstrap sample is equal to n. Uh, and n is 5, right? So now we have our bootstrap sample here. Next, we select D features that we want to pay attention to. So this is we set D to 3, so we'll just randomly select 3 different features to work with for our decision tree. So here we chose x2, x4, and x5 as our features. And so given this final data set, now we train a decision tree on this data set, and then that gives us one of our decision trees for our random forest. We repeat this same process 6 times by creating different bootstrap samples and then also selecting different features when we get to the step that we just finished. And once you do that, you'll have 6 small decision trees that can all work together and sort of aggregate their information together and output the answer of the random forest. So what is the purpose of doing this, which is the bootstrap sample and selecting D features? Well, essentially, we're decreasing the amount of information that we have in our training data set. We originally started our training set like this. It's pretty large, and we were able to reduce it to something small, right? So the amount of information that an individual decision tree can learn is not a lot. It can't learn the entire data set because we're not giving it the entire data set. So the fact that each individual decision tree is learning from smaller parts of the data and not the entire data set um, leads to lower amounts of overfitting, which can be beneficial for many applications. So going back to the slide about selecting the hyperparameters, n is the size of our bootstrap sample, right? So if you give n a high value, like um, close to the actual value of the training sets, then it's just going to be as bad as a regular decision tree in that it will still overfit to the data, except many different decision trees will overfit to the data, right? But if you give it a small n, maybe you only select 2 entities in your data set, then it may not be able to learn anything at all, right? So you have to strike a balance here between between a value of n that is that gives each individual decision tree a sufficient amount of data to learn from, but also a small enough n um, to prevent overfitting, which is what we were trying to do by creating a random forest in the first place. D, which was the number of features we allow our model to split on, is also a sort of similar, has a similar function of n in that it de-enriches the quality of our data set, right? Like it makes the data set harder to learn because we're eliminating some features that might potentially be very relevant. And so uh, you also want to strike a balance here between cutting out, too many variables by setting D um, to be very low. Then we have the problem that the decision tree can't learn anything because it doesn't have enough information to learn from. Um, and then we don't want to set it too high because then we're also getting closer to approximating what a single individual decision tree does. And so a common practice that you'll see implemented in most libraries is to set D to the square root of the total number of features. Um, and so yeah, that's basically all we have for random forest. If you understood how to create and train a decision tree, um, the process of creating a random forest is quite simple. You know, it's just adding a couple more steps, and then repeating the processes several times. But yeah, these are very useful, and they're very helpful in reducing the amount of overfitting that occurs. Thank you.